Hey everybody, and welcome back to Geology 112, Dinosaurs in the Age of Reptiles. This is the lecture content for week 4. And actually, at the end of this lecture series, or this lecture video, you're going to be seeing some information about our upcoming exam. So to kind of round out this first unit of the course, we're going to be talking about the relationship of time and the geologic record. One of the most important aspects of geological time is wrapping our head around just how enormous the amount of time we're talking about is. And this is really different than what we normally think about with time. Most of our lives are measured in decades. Our day-to-day lives are measured in minutes to hours. So when we start talking about millions or billions of years of time, it's sometimes a little hard to comprehend. However, the revelation of just how much time has passed in the history of our planet, approximately 4.6 billion years, was somewhat revolutionary to the geologic sciences, because it allows for that time that, as we know, most geological processes are very, very slow. So this allows for that kind of time. Furthermore, it also allows for the time that biological evolution requires. These are all generally slow processes. So it works out quite well that the estimates and measurements for the age of our planet accommodate this. It also fits us into the context of our universe. You see, the universe itself is approximately 13 to 14 billion years old, and our planet is around 4.6 billion, so it allows us to kind of see how planetary formation and planetary evolution take place on a universal context. And I think this concept of geologic time is what really is the one thing that people struggle with the most. Tell somebody that a volcano erupted, they can watch that, on YouTube. But talk about the rates of erosion or plate tectonics or biological evolution, that's not something we can just go outside and see and visualize. So getting a good understanding of geologic time can really open up the door quite a lot for other geologic concepts. To show you just kind of what type of time frame we're dealing with, let's take the entire history of Earth, about 4.5 billion years, and put it on a 24-hour clock. All right. So right at midnight or at 0 hour is when the Earth would form. Let's say that's 4.5 billion years ago. From then to 3 a.m. we have meteorite bombardment. That's what's happening as the planet is still cooling off. Our origins of life are around 4 to 3.8 billion years old, and this is mostly known through chemofossils. But our oldest true fossils we get around 5:36 in the morning. And then from about 6 a.m. to around 1:52 in the afternoon, we have abundant banded iron formations. These are geologic deposits that are forming, sedimentary deposits that are forming during this time, indicating oxygenation of our atmosphere. We get our first single-celled algae around 2 in the afternoon. And then notice at 6:08 p.m. would be around the time sexual reproduction starts. That means all the life prior to that was reproducing asexually, kind of like bacteria, essentially cloning themselves. However, after sexual reproduction is established as a means of reproduction among organisms, look how quickly things change. Seaweed, jellyfish, trilobites, land plants, coal swamps. Dinosaurs form or appear around 250 million years ago, and then human beings appearing just a few thousand years ago. So you can really see how much time has gone on and gone past during a 24-hour visualization such as this. But notice how 3/4 of the planet's history, there's not a lot going on. So there's two main ways that we talk about time in geology, and we've already alluded to some of these in previous lectures. First, we have relative age dating. And relative age dating is the first way that we talk about geologic time. And the way that we think about relative age is something we still use in our regular discussions. This is simply an order of events. It's a sequence based on logic and observation. Event A was followed by event B, followed by event C, and so on. This is very similar to what we talked about with our cross-cutting relationships and superposition and original horizontality and lateral continuity. We looked at those diagrams, we were able to put all those events in order. That is relative age dating. It's saying which event happened first, second, third, fourth, and so on. One way we might discuss this in terms of the geologic timescale would be to say something like the Devonian period preceded the Carboniferous. That's true. The Devonian period was before the Carboniferous. Doesn't tell us anything about amounts of time, but we still have that same relationship of which happened first, second, third, and fourth. Absolute age dating is, I think, what most people think of when they hear, age dating with geologic time. This gives us absolute values. It's calculating an actual number in years before present. This is a relatively new addition to the geologic sciences. It's only a few decades old. This is based on a knowledge of radioactive decay of isotopes, which we'll be getting into towards the end of this lecture. But this is dealing with the chemistry of materials that we're going to be looking at, specifically fossil material and the rocks surrounding them. And so it actually is a way of we can use to determine an actual age, and then we can work these two together. So for example, we know that the Devonian period is before the Carboniferous period. Well, the Devonian period began 405 million years ago. That's still before the Carboniferous, so that's still an accurate date. But we had a geologic timescale with periods and eras and so on before we knew the absolute values, the dates of any of these events. So we use these two types of time telling together. We can talk about the relative age of something and then constrain what an absolute age would be for that event as well. So let's start with a discussion on relative age dating. And actually, a majority of this lecture is going to deal with relative age dating because, again, this is the type of time discussions that geologists have had going back hundreds of years. The understanding of how old something is in terms of how many millions of years before present is, again, relatively new. So relative age dating deals with, again, the relative geologic time scale. Now, how do we compose a relative geologic timescale? Through some of the tools that we've already learned how to work with, such as superposition, original horizontality, lateral continuity, cross-cutting relationships, unconformities, inclusions, fossil succession, extinction. All of the concepts that we've talked about in previous lectures are the tools that we use to determine a relative geologic timescale. This yields a very precise sequence of events. However, it does not say how long or what duration events took place. So we can know that the rock on the bottom is relatively younger than the rocks above it. And that's true. We can see that this rock was originally deposited horizontally and was later uplifted and tilted or folded. But relative age dating doesn't tell us the duration. That we would need absolute age dating for that. So both forms of age dating are contributing something, but relative age dating is really setting that framework first. The very first geologic timescales, which were relative, again, were based on local exercises and then correlated. A geologist would go out and describe the sequence of rocks and events on their property, on their farm, and then they would go to another farm across the county and look for another outcrop of rock and correlate those together. They would use fossils to help link up the time, because remember, the concept of fossil succession deals with narrow ranges of fossil existences. So they would find the same fossils in rocks that are separated some distance. They would apply original horizontality and lateral continuity. They would discuss and describe the sedimentary rocks where the fossils are similar, and we would group those into time units and then give those units a name for a shorthand reference. Over time, these techniques were able to be applied to broader and larger regions and eventually globally as the techniques of relative age dating began to grow. And I want to point out that a lot of the techniques that were used in the 1800s to map rocks and figure out their relationships, we still use today. One of these tools is correlation, which is determining a unit of equivalence, in this case of geologic materials. It's saying that the rocks that I'm seeing on one plot of land correlate to the rocks at another, even if they're separated by some distance. Now, there's different ways that we can correlate things. Remember, correlation is simply finding a relationship of equivalence. So we can do this on wide scales of local outcrops to even continental and global scales. Physical continuity is really what we're doing here. We're saying that the rocks that we see at one location would have continued to another had they not been eroded or are buried. Just because you can't see them in front of you doesn't mean that they're not there. So it's figuring out how to trace beds over distances from some original point of inspection to others. Okay. One of the things we're looking for is lithologic similarity, but we have to be careful because as we discussed with sedimentary rocks, they represent ancient environments. So think about all the places today that you might be seeing sand accumulating, beaches, deserts, deltas, river channels. All of these are going to be producing sands, which someday could become sandstones. Yesterday there were sands being deposited. 1 million years ago there were sands being deposited. And 500 million years ago there were sands being deposited. So just because you find two sandstones at distance from each other doesn't mean that they correlate. You'd want to use fossils to help indicate that correlation because lithologic similarity can be misleading. But if you're looking at a sequence of events and you can correlate fossils or some other kind of tracer across it, it can be quite useful. Fossils really are the most important aspect here because we know that most species are now extinct, at least that have lived. Most of them didn't persist all the way to today. We can use fossils to say, well, this rock that has this fossil, we see the same fossil in a rock 100 miles away. Even if it's a different kind of rock, the presence of the same fossil in both units tells us those were formed within the range of that organism's existence. So that can be quite narrow. Now, since correlation is a process of demonstrating some form of equivalency, let's talk about the different ways that we can correlate geologic units. We can do lithostratigraphic correlation. This is linking one sequence of rocks to another that shows the same pattern. This is not always necessarily time equivalent because, again, you're correlating environments, not necessarily the same environments at the same interval of time. However, we have some clues we can look for that tell us that our geologic beds here are of close to the same age. Fossils, of course, are the big one, but we can also look for other evidence of instantaneous events, such as a coal bed, a glacial till, a volcanic ash bed, that tell us that this happened at a very specific interval of time. Biostratigraphic correlation is approaching time synchronicity, and this is using fossils in rocks rather than just the rocks themselves. And finally, we can use magnetism that is imprinted into rocks to tell us roughly the same time because magnetic fields have changed over time. So the rocks record those changes. And if we see the same change pattern in rocks over time, we can actually correlate those across. So let's look at some examples of the differences here. I've drawn a couple of little mini strat columns, and I'm still getting used to drawing on a computer screen, so pardon my lack of artistic quality. So here we have a sandstone, and here we have a shale, and then up here is a limestone. So these are some pretty common patterns. If you see a bunch of dots, that's a sandstone. Little dashed lines is a shale, and then any kind of a brick pattern is a limestone. So what we can do is, let's say this is some distance from column A over to column B. We can correlate and say that, well, here we have a shale that is overlaying a sandstone and underlaying a limestone, and we have the same thing on the other side. So we can correlate the contacts between these two and say that this shale correlates to this shale, and this limestone to this limestone, and this sandstone to this sandstone. This is lithologic correlation. We're just correlating rock types. All we're saying is that these connect. We're not saying anything about time, though. Now, if we go down to our lower figure, we have the same kind of strat column, sand, shale, limestone, but we have a fossil present in both of our columns. We want to do biostratigraphic correlation, and at that point, what we're going to do is say that this fossil correlates to this fossil. Notice they're in different types of sedimentary rocks, i.e. different environments. Over here, our fossil is in a shale, which would have been a deep water environment. And over here, it's in a sandstone, which is a more medium velocity type environment. However, what we're saying is these were deposited at more approximately the same time. So while in our upper figure, we can say that the shale correlates across, it didn't correlate at the same time. In other words, while this shale was being deposited, this sand was being deposited over here. So our first one is telling us about the relationship of sedimentary rocks. Down here, it's telling us about time. Now, sometimes over those large distances, there happens to be local erosion or non-deposition, and we get unconformities, which hopefully you remember from previous lectures. So on the column on the left, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different units with different types of fossils in them, and notice the order of the fossils. And then when we go over to the unit on the right, the stack on the right, we're missing 4 units in between. However, we can still correlate those across. Notice the way we kind of just thin those units out. We call that pinching out. They're still represented there as a disconformity, but they're not represented in the forms of the rocks or fossils. However, on the left, we see that this fossil is below this one. There's just a lot in between, and we have that same relationship here as well. So we can correlate over very large distances. If you've ever spent any time at any of these parks, Grand Canyon, Zion, or Bryce Canyon, it's interesting. You can get the entire, what we call the Grand Staircase, kind of an image here if you visit all of these parks. If you go to the Grand Canyon, the uppermost rocks you're going to see are the Kebab Limestone and the Moenkopi Formation, which are Permian and Triassic in age respectively. When you go to Zion, though, the oldest rocks that you see, meaning the ones at the bottom of the canyon at Zion, are the same rocks that are at the top of the Grand Canyon. The other rocks that you see exposed in the Grand Canyon are present at Zion, they're just not exposed. So you go to see, if you want to see the Moenkopi Formation at Grand Canyon, you go to the very top of the rim. If you want to see it at Zion, you go to the bottom of the canyon. At the top of Zion, we have the Carmel Formation. If you want to see the Carmel Formation, you have to go near the bottom of Bryce Canyon. And notice that when we put these all together, we have a Permian through Triassic, Jurassic, Cretaceous into the Tertiary conformable sequence. We have the entire Mesozoic era represented between these 3 parks. You just have to know where to look to see them. Now, there are a few stratigraphic terms and concepts that we need to understand before we continue any further. And this is the relationship between time, the change of the surface of the Earth, and environments. The most important and first of these is called the facies, defined as a lateral gradation of sedimentary units having distinctive sets of physical, chemical, and biological attributes due to a gradation of environments of deposition during a given time. That is a ridiculously long definition. So let's break that down to what it means. Lateral gradation of sedimentary units. Okay, we'll start with this one. Now, if you remember from when we talked about Steno's principles of stratigraphy, original lateral continuity was one of them, that units continue outward. They don't just abruptly stop, right? So even on some of our previous diagrams, you've seen units getting thinner and pinching out. That's what we mean by lateral gradation, okay? If you were to start driving from Oshkosh, Wisconsin, and you were going down south, let's say to a beach in Florida, at some point along the way, you would notice that the vegetation is subtly changing because the temperature is changing. It's not an abrupt wall where all of a sudden it starts getting warm and subtropical. Okay, it's going to be a slow gradation over time, laterally from one location to another. The same is true for our depositional environments. Okay, at some point you start to see a grade change as we go through. Okay, so this lateral gradation of sedimentary units that have distinctive sets of physical, chemical, and biological attributes. Well, let's see, a physical, chemical, and biological attribute of a sedimentary unit or sedimentary rock would be something like grain size and grain shape, sorting and maturity, some of the things that you used when you were identifying sedimentary rocks during Lab Unit 1. Chemical attributes would be the types of minerals that make these sedimentary units up. Again, something you used when looking at sedimentary rocks. And biological attributes. In other words, what kind of fossils do we have in them? Why? So this first part of the definition, a lateral gradation of sedimentary units having distinctive sets of physical, chemical, and biological attributes. In other words, that means the change in environments as represented by sedimentary rocks, laterally changing from one location to the next. And this is due to that gradual change of environments of deposition during a given time. Okay, so if you go to the beach and you look down at your feet and there's sand with shells in it, and it's a quartz sand and the grains are really round, that's a facies. That's a beach facies. If you go to a river channel and you see mud on the floodplains and you see gravel in the bottom of the riverbed and sand on the point bar next to the channel, those are all fluvial facies. If you go to the desert and you see more sand, but it's in huge dunes and the grains are rounded, and when you look at them under a microscope, they look etched in frost from blowing around in the wind, that's a desert facies. Each facies is a lateral gradation of sedimentary units having distinct sets of physical, chemical, and biological attributes due to the change or gradation in environments of deposition during a given time. Every depositional environment has characteristics of a facies. But what we talk about with facies is how they change gradually from one location to another. Not only in space from one place to another, but how they change through time. Last week when we talked a little bit about correlation, or not correlation, but unconformities, we talked about how here in Oshkosh, if you strip away the topsoil, you have glacial lake deposits. That's a facies. That's a glacial lake facies. And underneath that you have early Paleozoic limestones that are considerably older. Well, yes, those are marine facies. So we have a marine facies that's capped by a glacial lake facies. That is looking at a change in facies through time. And that brings us to the concept of Walter's law, which states that facies are adjacent vertically just as they are adjacent laterally. Laterally is telling you what's changing from environment to environment. Vertical changes are telling you what's happening over time. Now, this is a little abstract, so we're going to try to explain it better with some diagrams. So Walter's law pretty much states that the sequence of events that you see in an outcrop of rocks, you're looking at changes in environments over time. You can see the same pattern laterally if you were able to visualize the entire transect. So up here in the corner, I have a strat column where we have a sandstone that's deposited during time 1, we have a limestone deposited during time 2, and we have a shale deposited during time 3. So you could go out into the field and look at a quarry and see these different types of rock units stacked on top of each other. But you are looking at the change in environments at one location over 3 intervals of time. What Walter's law states is that if you could go back in time and just see time 1 being deposited, the same rocks that you're going to see deposited in time 2 and time 3 will be adjacent to time 1. So this is what we mean. Here's time 1. If I'm standing right here on this beach dune, just offshore from me, there's a carbonate reef forming, producing that limestone. And further out, still in deeper water, we're depositing shale. Well, let's say that we look at the pattern of that and notice that the pattern goes from sand to limestone to shale, but this is just in one interval of time. Notice our sequence up in the corner. It's the same pattern through time. And here's what we can do to see that. Here's time 2. Now we see that the limestone is being deposited on top of the sandstone, and that's because sea level went up. And on top of where we used to deposit limestone, we're now depositing shale. And then if we go into time 3, we see an even more continued increase in sea level, and now we're flooding everything. But notice the same pattern is present when we look here over time. This way, it's the same pattern we see this way. This is looking at environments And this is looking at time. Changes in environments over time versus changes of environments over distance. Time 1 is giving you images of changes over distance during an interval of time. The sequence of all three are telling you at one location how those environments changed over time. So we can look at two different aspects with Walter's law. And this brings us to changes of sea level, which we call transgressions and regressions. We aren't just going to say raise or lower of sea level, because it's more complicated than that. If the shoreline is moving landward, that's a transgression. It's a relative rise in sea level. It could also be flooding. In any case, you're seeing the shoreline encroach onto the land. We call that a transgression. Alternatively, if our shoreline is moving seaward and we are exposing more shoreline, that's a relative fall in sea level or continental drainage, and we call that a regression. So when we discuss sea level change over time, it's in terms of transgressions and regressions, sea level going up and going back down, relatively. Now, when you're looking at a stack of geologic units over time, you're in a quarry and you're looking at a stack of rocks on top of each other, sedimentary rocks. You can actually identify whether those rocks represent a transgression or a regression because they produce very distinct sequences over time. A transgression will have your near-shore facies overlain by your offshore facies. Okay. So, in other words, your near-shore facies will be anything that's closer to the shore, so sands and gravels will be overlain by your offshore facies, which would be things like limestones and muds. Your regressions will be the opposite. Your offshore facies will be capped and overlain by near-shore facies. So you'll start out with limestone or shale, and on top of it you'll have sand or gravel. Because the size of the grain tells us something about the depth of the water. Shallow water environments are usually represented by more coarse grain material. Deep water environments usually more represented by fine grain material. Transgressions also have this bizarre phenomenon where they will produce individual rock units that become younger as you go towards the land direction. We call this a time transgressive phenomenon. And we'll talk more about that here in a minute. So I want to emphasize the differences between a transgression and a regression sequence a little bit more. With a regression, again, you are getting your near-shore facies that are going to be relatively more coarse, overlaying or capping your offshore facies, your deeper water facies. So as a result, when you go from the bottom to the top of one of these relative sea level fall sequences, you see that sediment becomes more coarse as you go up. So it's a coarsening upward sequence. Now a transgression, what you're seeing is the opposite. You're starting out with shallow water facies, near-shore facies, and they're being buried by offshore facies. So in this case, you start out with sands and gravels, and then it gets progressively finer as you go upward. So a regression shows a coarsening upward sequence, and a transgression forms a fining upward sequence. And this is how we can identify, looking at sequences of rocks in the field, whether they represent a change in sea level with it relatively going up or relatively going down. Let's talk a little bit about sea level changes. So when we say transgression and regression, we're really talking about a shift of the shoreline, right? We say a relative change in sea level. And here's why we can't just say sea level went up or sea level went down, because it has to do with what's actually changing to give the appearance of a change in sea level. We can describe these types of changes in effects of isostatic or eustatic changes. What we call an isostatic change is when you have a relative sea level change that's caused by the ground itself, the continental mass, changing in elevation. So imagine a mountain range that's uplifting. As it uplifts and gets taller and taller, any water that's going to be encroaching next to it is going to appear to go down. But the ground is actually moving, the water isn't doing anything. A eustatic effect is when we actually change the amount of water or the shape of an ocean basin. In this case, yes, the water level changes. So a change in Isostatic versus eustatic effects are really important when we're trying to decipher which kind of sea level change we're seeing. So isostatic effects are usually tectonically related. You have uplift or subsidence of the ground of the continental mass itself. A eustatic effect is when we add or remove water from the oceans. That's going to raise and lower that as well. So here we can see in this diagram an isostatic effect. We're going from the top down to the bottom. We can see that the ground is moving, but if you pay really close attention to our isostatic models, the sea level itself isn't doing anything, but the land mass is rising. So if you were standing on the land that is moving upward, to you it would look like sea level is falling. However, let's take a look at the isostatic or the eustatic effect on the right. In this case, our ground mass isn't really doing anything, but the water level itself is going up as we go from the top to the bottom. Okay, so in this case, we're not actually changing anything with the land mass, we're changing the amount of water in the ocean basin, in this case increasing it, so we would see an increase in sea level. Okay. So isostatic effects are related to tectonics, eustatic effects are related to climate, because one of the best ways and easiest ways to change the amount of water in the oceans is to make things warm or cold. If you make things very cold, you have evaporation of ocean water, and it forms snow and ice that gets trapped on the continents in the form of glaciers, and now you've removed water from the oceans and stored it on the land. That's going to decrease global sea level eustatically. And when you melt that ice during warm seasons and conditions, all that water goes rushing back to the oceans, and you've raised eustatic sea level. Similarly, if you have a mountain range uplifting, then you have a fall of isostatic sea level. If you have land that's being suppressed down and it's getting flooded, you're going to see an isostatic sea level rise. So we talk about sea level rise, transgressions, and regressions as relative because there's some interplay between isostatic and eustatic effects at any time going on. Now, let's talk about time units a little bit. One type of time unit is something we call a chronostratigraphic unit or a time stratigraphic unit. The most fundamental unit of this is the system, the geologic system. A system is defined as all of the rocks and geologic materials that were deposited and formed during a certain interval of time or during that interval of system. Okay? So we define these based on rocks of a particular area that we call a stratotype, and then we recognize them elsewhere and correlate them based on their fossil content. We can break a system down into upper, middle, and lower sections, or we can group them into erythems and ionothems, or break down those upper and middle lower areas into series and stages. Okay? So this would be equivalent of if you saved every piece of paper, every book, every note that you ever had during your years in college. That would be, and you stack them up from freshman year at the bottom to super senior year at the top. That would be a chronostratigraphic system. You would talk about the lower portions, the middle portions, or the upper portions of that stack. That is materials that are representing a time. They represent your time in college. In this case, a system will represent a period of time. It represents an interval when all of these things were happening. We compare that with what we call a geochronologic unit, which is just fundamental pure time. It doesn't have any tangible evidence. It is simply an abstract unit. Well, we can say that a geochronologic unit is represented equally by a chronostratigraphic unit. This would just be the years in which you were in college. From what date to what date of a graduation. So we modify these by early, middle, and late because they're abstract time. And think about it. We already do this still. If you're talking about what you're doing on Friday, what you're going to say is, well, early in the morning I have to do this, and then middle of the day I have to do this, and then in the evening, later in the evening, I have to go to hopefully not a in-person party. A chronostratigraphic unit would be the evidence of that. Your receipts, your documents, your whatever evidence it is that you're doing it. Okay? So we break down these abstract geochronologic units into era, eon, and we can, or group them to that, and then we can break them down to epoch and age. Okay, so again, geochronologic units are just time. That's like saying Friday. Early in the day, late in the day. Chronostratigraphic units are the physical products that result of you existing during that time, whether it's trash or notes or receipts or whatever. In the terms of geology, rocks, fossils, and geochemical signatures are making up the chronostratigraphic unit of the system. And that system represents a geologic period. So, geochronologic versus chronostratigraphic. Let's start with our most basic units. The geochronologic period is represented by the chronostratigraphic system. We can take periods and group them into eras. All of that time represented in those eras are represented by erothems, chronostratigraphically. Or we can take a period, an interval of time, and break it down into epochs, or ages, which chronostratigraphically would be represented by series and stages. But we're going to use the same names. The Jurassic period is represented by the Jurassic system. The period is the abstract interval of time. The system is the evidence for it. It's the rocks, fossils, and chemical signatures that were produced during that time. So once again, to demonstrate this equivalence, eonothems to eons, Phanerozoic, for example. So all of the life on Earth is represented in the Phanerozoic eon, which actually we represent as evidence seen in the Phanerozoic eonothem. One of the eras in the Phanerozoic eon is the Mesozoic era. That's represented by the Mesozoic erothem. That's all the geologic materials from 250 to about 65 million years ago. The Jurassic is one period in the Mesozoic era, and it's represented by all of the rocks and fossils from the Jurassic, known as the Jurassic system. We can break down the Jurassic period into different epochs, such as upper or late. See, now if we're talking about time, it's going to be the late Jurassic, which is going to be represented by the upper Jurassic series, the rocks, the uppermost rocks of the Jurassic. And then the Tithonian would be the age of one of those epochs, and chronostratigraphically we call that the Tithonian stage. So we use the same example names for these, but whether you say eon or eonothem or period or system makes a big difference. Are you talking about an abstract chunk of time, or are you talking about how we know about that abstract chunk of time? So we have our geochronologic time units. We have our chronostratigraphic time rock units. What about just rock units? And that would be lithostratigraphy, lithostratigraphic units. So the fundamental unit of this is the geologic formation. Now, a formation is defined as having distinctive lithology with recognizable contacts, with underlying and overlying units that can be traced laterally, as in can be correlated, with no regards for time boundaries. So what we actually mean by this is, let's think about it. If I have a long unit of sandstone, okay, a distinctive lithology, okay, with recognizable contacts, because underneath, let's say we have a shale, and on top we have a conglomerate, which is this pebbly texture. Okay. Our sandstone formation in between there, it has a distinctive lithology with recognizable contacts, underlying and overlying units that can be traced, and it has no regards for time boundaries because we're not talking about fossils at this point. It's just the rock units themselves. So another way of thinking about this would be the formation is made up of very distinct lithology that grades from one location to another. Formations are made of facies over time. We can take our formations and we can divide those up into members of a formation, and members can be divided into beds. Or we can take numerous formations and group them together into groups, or take numerous groups and form supergroups. Formations are usually time transgressive. This is what we were talking about with transgressive sequences, that as you get a relative sea level rise, you are burying the previous unit and moving everything landward, which means that it's going to be younger landward than it is seaward. So as a result, what we call the Hell Creek Formation, where we find our T-Rexes and Triceratops fossils in the American West, is actually younger in the West than in the East in some places because of this time transgressive phenomenon. So again, when we describe lithostratigraphic units, we're talking about geologic formations as the fundamental unit. And we can break those down into members, or we can combine them into groups. These are usually given a name that is in reference to where that formation was first described or identified, which is sometimes called a type locality. So when we describe our rock units, a formation name is the location where it was first described or best discovered, and then what type of rock it is, or if it's an assemblage of related strata, like similar types of rocks that are all part of the same type of depositional environment, we can just use the word formation. So the Burlington Limestone, the Juniata Formation, the Hell Creek Formation. Hell Creek Formation was named after Hell Creek, Montana. It's sands and gravels and silts and clays, which all represent river systems. The Pierre Shale is named after its first type locality in Pierre, North Dakota. The Galena Dolostone is originally described from Galena, Illinois, but we have Galena Formation, Galena Dolostone in Wisconsin. So these can be, they can span great distances because of original horizontality and lateral continuity. And then we have the way that we can correlate things based just on fossils, where we're not going to worry too much about what kind of rock it's in, because we're doing biostratigraphy here. We're using fossils to provide relative age dates. And this is entirely based on the concept of fossil succession. However, there's a certain kind of fossil we want to use for this. Not every fossil is really, really good for biostratigraphy. The best thing to use is what's called an index fossil. An index fossil is a fossil organism that is very well defined with morphology, so it's not going to be something you're going to accidentally get confused with something else. It's very distinct. It's a short-lived species. If you want to use fossils to tell time, it helps if your fossils haven't been around for billions and billions of years. In this case, you want them to be around for a very short period of time, because it will represent that period of time. And geographically widespread distribution. You don't want these fossils to only be found in one place. You want them to have a short, narrow window of time when they existed, but they were successful enough to be cosmopolitan all around the planet and easy to identify. So as a result, dinosaurs actually don't make very good index fossils, because while some of them do have well-defined morphological characteristics and can have a short-lived species that can not be around for more than a couple million years, they're not all geographically widespread. For example, Triceratops is pretty much a North American taxa. Apatosaurus is a North American taxa. So we can't use it for correlating around the world or biostratigraphy around the world when you only find them in one location or a few locations. As a result, most of our index fossils are invertebrates, or in some cases, microfossils. Now, these are all fossils that are easy to identify if you happen to be studying fossils. They all have a very distinct interval of time in which they existed, and they're pretty widespread in their distribution. So for example, the trilobite you see at the bottom, Paradoxodus pinus from the Cambrian, that's only around in the Cambrian. We define the Cambrian based on that. So if you find that fossil, you know that's a Cambrian rock that it's encased in. We can also use magnetic signatures to help us tell time in the geologic record. So these are going to have aspects of biostratigraphic and chronostratigraphic and geochronologic units all together, but we're using what we call magnetopolarity zones, which are essentially time synchronous, because this is identifying when the Earth's magnetic field changed, which doesn't happen over millions of years. It happens very, very quickly. So anytime we are erupting basalt at the ocean floor, the iron rich crystals in that basalt are being magnetized by our Earth's magnetic field. And just the way that a compass works, where you have a magnetized needle that points to magnetic north, these little crystals orient themselves to have a north magnetic polarity pointing to magnetic north. So you can actually take rocks from the ocean floor, from the basaltic crust, and figure out what direction magnetic north was when that rock was forming. You can also tell when it reversed, when magnetic north was pointing to geographic south, which happens occasionally. We get these magnetic reversals. So we can look at rocks over time and see how they flip back and forth, and this allows us to pretty much have a pure synchronous identification of time with these particular types of rocks. It's common to use with igneous rocks, but we have found ways of doing this with sedimentary rocks if they have enough magnetizable metallic minerals in them. And so we put all that together and we get our relative geologic timescale. So don't worry about any of the numbers in millions of years before present, but the Precambrian existing before the Phanerozoic, and the Phanerozoic being made up of the Paleozoic, Mesozoic, and Cenozoic eras, and then all of the periods that make up those eras, we had that organized before we knew how many millions or billions of years ago an event happened. Because the geologic timescale, remember, is based on fossil occurrences and extinctions. What we call Ordovician time is the time in which a certain collection of fossils existed in life. When what we call the Silurian period or system is when a different group of organisms were around. We see a change in the plants and animals over time. Okay? We don't base it on changes in rock type. We don't base it on time alone. It's based on fossil occurrences and extinctions. It would be really nice to know when those events happened, and that's where relative age dating needs to rely a bit on absolute age dating, as far as when an absolute age, but the sequence of events is still the same. So here's a more simplified version of that geologic timescale you just saw, where we have the Archean, Proterozoic, Phanerozoic, and the eras and so on. Okay, those major changes that we see are from changes in the fossil record. It's when we see a big turnover or change in the types of fossils we find. That's how we define these units. The relative timescale does not give us numerical ages, though. We need a different tool to study how many millions or billions of years ago these periods existed and these organisms existed. So we have a relative timescale that tells us an order of events, and an absolute timescale technique that tells us when, in absolute terms, those events occurred. So that brings us to absolute age dating, where we obtain a numerical value to the relative geologic timescale. Now, absolute age determination is based on radiometric dating techniques, which gives us years before present. Essentially, we couldn't figure this out until we already had a handle on radiometric chemistry, because this is going on at the subatomic level of our rocks. And there have been a lot of different methods that have been used to try to figure out how old the Earth is. Researchers would look at the thickness of sedimentary rocks and then go to a river today and see how long it takes for sediment to accumulate. Well, that's making the assumption that it's uniform throughout time, which it's certainly not. It also doesn't take erosion and unconformities into consideration. There was a kind of a cool concept that was applied where it was looking at the cooling of the planet and looking at the cooling rates of various metal spheres. A really ingenious idea, but ultimately it makes the assumption that the Earth is initially molten with no other heat source, so it doesn't take radioactivity into consideration. So it's very, very wrong, but it's clever. And then, or looking at the saltiness of the oceans and figuring out how that contributes to our buildup of salt deposits over time. Again, it's assuming climate and salinity are the same over time from one location to another, which they're certainly not. Radioactivity, though, has proved to be the best because you're dealing with something going on at the subatomic level that can't just easily be changed unless the material is completely destroyed. So let's do a quick recap of some very basic concepts in chemistry to help us learn about this a little bit more. We're looking at radioactive decay, which is the change of one element to another. Okay, for example, turning uranium to lead. Okay, what we call the parent element is the radioactive material we're starting with. The daughter element is the stable product that we end with. And the rate at which we go from parent to daughter, the decay rate, is going to be constant. It doesn't just change because the environment changes. It stays constant. Again, this is going on at the subatomic level within the nucleus of an atom. So there's really nothing short of destroying it completely that's going to modify that decay rate. So as the parent element decays, the amount of parent material decreases, the same rate that the daughter element increases, because one's turning into another. Okay, so we have a ratio of parent to daughter elements. And again, unaffected by heat or pressure. So when you look at the rate at which that transformation is taking place within the nucleus of the atom of one of these minerals in a rock, you're seeing the parent material decrease at the same rate that the daughter material is increasing, and you can't change that with heat or pressure, not short of destroying it. So what are some of the elements on the periodic table that decay? Uranium, thorium, potassium, rubidium. So any minerals that have these elements in them, like feldspars, zircons, biotites, muscovites, amphiboles, and many, many others, we can date. And they lead to products like lead, strontium, argon, and helium. So we look at, for example, the ratio of uranium to lead in a radioactive element in a mineral, and we can get an idea. If we know that decay rate, we can get an idea of how old it is. So what can we date? Well, most igneous rocks, because what we're dating are mineral crystals that formed at the time of cooling. Some metamorphic rocks can be dated if there are minerals that formed during metamorphism. However, we can't date a lot of sedimentary rocks directly. And that's because, if you recall, sedimentary rocks are recycled products of previously existing rocks. If I want to date a sandstone, essentially what I'm trying to date is when was this sand deposited. That would be the age of a sandstone. But if I did radioactive dating on a sandstone, I'm going to be getting a result of when that sand grain formed inside of the granite parent rock it came from, which is very different in time and space from what I'd be looking at a sandstone. So that means we have to rely on situations where we have something in that sedimentary unit that we can date, like a volcanic ash layer. So if I have a layer of sand, and let's say there's a fossil in it, and here's the sand grains around it. I can't date that, because if I take one of those sand grains and date them, it's not going to tell me the age of the deposit. It's going to tell me when that sand grain crystallized in its parent rock like granite. But let's say right above that sand we have an ash deposit. That has zircons in it. I can date those. And let's say underneath that sandstone there's a basalt from a volcanic eruption. I can date that too. There's feldspars in there that I can use. So let's say that my basalt gives me a date of 100 million years ago. And my ash deposit tells me 90 million years ago. That means that this fossil and the sediments surrounding it were deposited between 100 and 90 million years ago. So what we have there is a 10 million year range for when that unit was deposited. So we can use radiometric and relative age dating together, because what we did here is actually say, well, we know that the basalt is older because it's on the bottom, and then we had the sand, and then we had the ash deposit. Well, I can date two of those, and that I can then constrain the age of the sandstone and anything in it, including fossils, by combining these two dating techniques. So let's look a little bit at radioactivity. Radioactivity is defined as a spontaneous change or decay in the nucleus of an atom. Now, what's in the nucleus of an atom? Well, you have protons and neutrons. And then around the nucleus, you have your electrons. We're not going to worry about electrons right now. Protons have an electrical charge of +1 and a mass of 1. Neutrons, being neutral, have no charge, but they also have a mass of 1. So if you look at a periodic table, you'll see an atomic number and an atomic mass. The atomic number is simply the number of protons in the nucleus. The atomic mass is the number of protons plus the number of neutrons. And again, electrons we're not going to worry about. Okay, so that's for any basic atom. Okay, hydrogen, for example, the first element on the periodic table, if you want to Google that or Google a periodic table. Okay, hydrogen is, very simply put, has an atomic number of 1 because it has 1 proton in its nucleus. And it has an atomic mass of 1.088, which essentially is still 1 because it's essentially just a proton with then a neutral electron configuration charge. Okay. When we look at helium as an element, helium is the second element on the periodic table. Okay. So helium has atomic number of 2. It has 1 proton, 1 neutron, and its atomic mass is 4. Okay, atomic mass is 4 because we're going to have 2 of each. So what is then an isotope? An isotope is an element with a different number of neutrons in its nucleus, different than what it should have on the periodic table. We measure radioactive decay rates in terms of half-lives. The half-life, and this gets confusing, is the amount of time for half of the parent radioactive elements to decay into stable daughter elements. Okay. Doesn't matter how many atoms we start with, we're looking at a rule of halves, so we're always dealing with a ratio. So here's a couple of half-lives. Rubidium-87 decays at a half-life of 47 billion years. Well, considering our universe is only about 13 or 14 billion years old, we haven't even gone through one half-life of rubidium-87. Uranium-238 has a half-life of 4.5 billion years. Potassium-40, 1.3 billion years. Uranium-235, about 713 million years. And then carbon-14, which you may have heard of if dealing with archaeological materials, around 5,730 years. So let's look at an example of radiometric dating. We start out with potassium-40, which is radioactive, and it will decay to make argon-40. So imagine an hourglass with sand in it. The potassium is in the top of that hourglass, and the argon is going to be in the bottom. When that starts, when that mineral crystallizes, there is 0 argon. We have radioactive potassium, and none of it has converted to argon yet. So we have all the sand in the top, none in the bottom. Every time a grain falls through into the lower chamber, that turns into argon. So imagine that our hourglass is like a feldspar, or an amphibole, or a biotite, or a muscovite, anything that's going to have potassium-40 in it. So here we go. Let's look at a chart for this, where at the 0 hour, 0 half-lives, we have 100% parent and 0% daughter. After the first half-life, we've removed half of the parent material. We're now at 50-50 with parent to daughter. At the second half-life, we're at 25% parent, 75% daughter. And then we continue on. At half-life 3, we're only left with 12.5% parent. At the fourth half-life, 6.25% parent. And once you get past that, you're not really calculating much for half-lives anymore. At some point, you get to a point where there's just not enough to study and measure. So we simply analyze that mineral, look at the ratio of parent to daughter, and multiply the appropriate half-life, and we can get an age. So for example, if I had a fossilized bone from an archaeological site, so it's relatively recent, and I look at this bone and I see that half of the carbon-13 in it has decayed to a stable form, 50%. Well, that's one half-life. And the half-life for carbon-14 is 5,700 years. So I would then say it's gone through one half-life, that's how old it is. If I only had 25% of the parent material, I would multiply that half-life by 2. If I only had 12.5%, I'd multiply it by 3, and so on. So we can determine these absolute ages by looking at the igneous materials and sometimes metamorphic materials that are encased in and around our sedimentary rocks, which encase fossils. And so we can get a collective geologic timescale from this, where we go from the beginning of Earth's history at 4.5 billion years ago. The Paleozoic and Phanerozoic eon began 540 million years ago. The Mesozoic era spanned from approximately 248 to about 66 million years old. And at 66 million years old, 65 million years old is when we had the Cretaceous extinction, and the Cenozoic era, our current era, began. So we're combining absolute and relative age dating techniques together. And actually, this brings us to the end of the content of the material for Exam 1, which we'll be having here shortly. So to prepare you for the exam, we're going to have a couple opportunities to review this material. Now, I know that not everybody is comfortable meeting face-to-face, and I know that not everybody likes the online format, so we're going to try to appease everybody. On Wednesday, September 30th, during our regularly scheduled class time, which is 1:50 to 2:50, I will be holding a virtual review session on Microsoft Teams or Collaborate Ultra. We'll figure out what works better. And we'll hold that hour of time on Wednesday of the 30th to discuss anything you want to about the exam or about the content that we've already covered. Now, if you would like to meet face-to-face on Friday, October 2nd, I will be holding an in-person review session again at 1:50 to 2:50 in Sage 4232, which is our actual scheduled classroom for times when we want to meet like this. I want to make it clear that neither of these are mandatory. This is something I'm just offering to try to help get people ready for the exam. And I encourage you to participate in one or the other, but it is not mandatory. That being said, so Exam 1 will launch on Canvas on Friday, October 2nd at 5 p.m. Okay, so it's an entirely online exam. It will close on 11:59 p.m. on Monday the 5th. So you have Friday evening, Saturday, Sunday, and all day into the evening of Monday to complete the exam. Once you begin the exam, though, you have 60 minutes to complete it. So you need to make sure that you kind of have some of this information at the ready. I know you're going to use your book and notes, and that's totally fine. But the exam is specifically going to be structured where if you only have an hour to do this, so if you haven't cracked open your notes or anything or reviewed any of the content by the time the exam comes up, you might find 60 minutes is a bit of a tight squeeze. So you need to be prepared so you know where to look for things. The exam will have multiple choice and true-false question, an essay question, and a fill-in-the-blank question. It's worth 100 points total. Again, you can use your books and notes and class materials, but I want you and encourage you to be familiar with the content before you hit go on the exam, so that way you can use that time more efficiently. That essay question, the way that I do my exams is I will always throw an essay question on there because my goal is to try to understand what you understand about this content, and that can't always be conveyed through multiple choice. So I am going to ask you to fill out an essay question on this exam, and I know that's a lot to ask, like, wow, how do I know what this essay question is going to be on? Well, I'll tell you, it's going to be one of these 4 options, and I will choose one at random and put it on the exam. If that essay question asks you to draw or sketch at any time during the semester, the essay upload thing for Canvas does allow you to include sketches and diagrams. So if you sketch something on the computer or you sketch it on paper and you take a photo of it or scan it, whatever, that's fine. Email it to me, that's fine too. Okay. Again, means that you should be prepared ahead of time. So here are the 4 potential essay topics or questions that I want you to think about as you prepare your notes for exams. 1, draw examples and discuss the formation of 3 different unconformities, like we talked about in class. Discuss different forms of fossilization, including permineralization, recrystallization, replacement, molds, casts, and Steinkerns. Discuss how Darwin's mechanism of natural selection, including his observation and inferences, contributes to the theory of biological evolution. And finally, draw and discuss transgressive and regressive sequences as they relate to Walter's law and facies. Now, I would be picking one of these topics for the essay question, but you can be sure that the other 3 topics will be covered in the forms of other questions on the exam, whether as multiple choice, true, false, or a fill-in-the-blank section. It is in your best interest to take the next couple of days and practice writing out what you would write for any of these questions. Sketch what you would sketch. That way, when the exam comes up, and here's the essay question, you already have it ready to go. Now, the other content that's not covered as an essay question will help you because you've prepared. You'll already know that information for the other kinds of questions. So while these 4 topics don't cover all of the content we've discussed, it covers a vast majority of it, or a significant portion of it. So I strongly encourage you to go ahead and come up with an essay response and sketches for all 4 of these. And when it's time for the exam to launch, you're all ready to go on that end. So in the meantime, I will look forward to seeing everybody at a review session at one form or another. And if you have any questions as we approach the exam, please don't hesitate to ask. Thanks.